Hello, welcome to the course SJPH51B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. In today's class, we will calculate moment of inertia of some simple objects. If you recollect the discussion in the previous class, we have derived an equation for moment of inertia of a rigid body. Remember, in the case of rigid body, there is a continuous distribution of mass. So instead of a summation, we use an integral equation. So I equal to integral rho squared dm, where rho is the perpendicular distance from the axis with respect to which we are calculating the moment of inertia, and dm is the mass element. You can write the mass element in terms of density and the corresponding volume. So dm equal to density W multiplied by volume element dV. So this is the general formula for mass element in the three-dimensional case. So let's take some simple objects. First one, a uniform thin stick of mass m and length L, and we need to calculate the moment of inertia about an axis which passes through the midpoint perpendicular to the stick. Okay, so this is the stick of length L and mass m, and at the midpoint you have an axis perpendicular to the stick. Okay, so you're asked to find out moment of inertia about this particular axis. So if the total length is L, so this is the midpoint, so this side is minus L by 2 and this side is plus L by 2. Second thing, this is a one-dimensional problem because you have a thin stick here, its thickness is negligible, so the only relevant dimension is the length dimension, which you take it as the x direction. Okay, and perpendicular distance with respect to the axis is also x. So moment of inertia I equal to integral from minus L by 2 to plus L by 2. So rho square, you have x square dm. Now, how do you calculate the mass element dm? Mass element is nothing but density multiplied by the corresponding volume element. As I said, this is a one-dimensional problem, so there is no volume here, only the relevant dimension here is the length. Okay, so usually in three-dimensional you define density as mass by volume. Since this is a one-dimensional problem, you have a line density which is defined as mass per length. So total mass is m, total length is L, so line density is m by L. This is your W. And instead of volume element, you have the length element, which is dx here. So dm is nothing but the mass corresponding to length segment dx. Okay, so once you have dm, substitute back into the integral equation. So I equal to integral x square m by L dx. M by L is a constant, take it outside the integral, and integral of x square is x cube by 3. Apply the limits, you get moment of inertia as 1 over 12 ml square. So this is the case when the axis passes through the midpoint. So what happens if we shift this axis to one of the ends? So how does the moment of inertia change? Because we know that in angular motion, moment of inertia or angular momentum or torque, all these parameters depend on the choice of our origin. So obviously when you shift the axis, the moment of inertia is going to vary. So let's assume that now we have axis at the left end. So if you take it as the 0 point, now the total length is L. So your limit of integration changes from minus L by 2 to plus L by 2 in the previous case to 0 to L. That's the only change here. And dm is same as before. This is the line density m by L multiplied by the line element dx. So you have I equal to m over L integral 0 to Lx square dx. I do this integration, apply the limits, you get the value 1 over 3 ml square. So you can see the same system depending on the choice of the origin or depending on the choice of the axis, the moment of inertia value varies. Third one, a uniform thin hoop. Hoop is like a ring with certain width. Okay. A thin hoop of mass m and radius r, you are asked to find out moment of inertia about an axis which passes through the center as shown in this figure, perpendicular to the plane of the loop. Okay. So start with the general equation for moment of inertia, I equal to integral rho square dm. Now we need to calculate the mass element dm. So you have a circular hoop here, choose a small segment, and this thickness is negligible because you have a thin hoop. So essentially this is a length segment. Okay. So you are choosing a small segment of length, call it as ds. And what's going to be the mass element? Mass is nothing but density multiplied by the corresponding length. Now, how do you calculate density? Remember, since the only relevant dimension is this circular length or the periphery, what we are talking about is the line density. You know how to calculate the line density. This is total mass m divided by total length. You're talking about a circle of radius r here, so the total length is going to be the perimeter 2 pi r. So line density is m divided by 2 pi r. Multiply it with the line segment ds, you get the corresponding mass element dm. Now what about rho? Rho is a perpendicular distance from the axis to the line segment. So here the perpendicular distance is nothing but the radius r, so rho is r. And what are the limits of integration? You start from 0 all the way to the complete circle, which is 2 pi r. So I is integral 0 to 2 pi r. Instead of rho square you have r square, instead of dm you have m over 2 pi r ds. Here r square m by 2 pi r, all these are constants, take it outside the integral. Integral of ds is s, apply the limits, you get m r square. So this is the moment of inertia of a uniform thin hoop about an axis which passes through the center. Next one is a uniform disk of mass m and radius capital R. Once again, you are asked to find out moment of inertia about an axis which passes through the center perpendicular to the plane of the disk. Now, since we already know the moment of inertia of a hoop, what we can do is we can subdivide the disk into a series of thin hoops with radius rho and width d rho. Okay, so you can imagine that the disk is made up of a number of thin hoops. Okay. So we choose one particular hoop, rho is the radius, this is a variable, and thickness is d rho. And we know how to calculate the moment of inertia, right? So you calculate the moment of inertia of this particular hoop, then you calculate the next one. Finally, you add up all these individual moments, you get the total moment of inertia. Or instead of a summation, if you have a large number of hoops, you can do an integration. So the total moment of inertia I is given by integral over di, where di is the moment of inertia of each individual hoop. Okay. Now, how do you calculate di? One thing you have to remember, a disk, it has a certain surface area. So in the previous case, when we considered a hoop, we were talking about thin hoop, its surface area is negligible. But in this case, we need to consider the surface area. In other words, your density will be defined in terms of surface density instead of line density. So let's first calculate what is the surface area of this particular strip. So it has a radius of rho, so the perimeter is 2 pi rho, and the width is d rho. When you multiply the perimeter with the width, you get the surface area. So surface area dA is 2 pi rho d rho. Now the mass element corresponding to this particular strip, as I said, mass is nothing but density multiplied by the corresponding dimension. Here, since we are talking about the surface, this is surface density, mass divided by total area A. This is surface density multiplied by the corresponding dimension, which is the area element dA. So dm is m by a multiplied by dA. Substitute for dA, you get m2 pi rho d rho by pi r square. So pi cancel, you have 2m rho d rho by r square. So this is dm, and what is the moment of inertia of this particular strip with respect to the axis? This is going to be rho square dm, which is 2m rho cube d rho by r square. So this is for one individual hoop. So if you want to calculate the total moment of inertia of this entire disk, you need to integrate this. And what are the limits of the integral? You start from the center 0 all the way to the outermost hoop, which is at a distance r from the center. So the limits of integral are from 0 to r, 2m rho cube d rho by r square. 2m r square, all is a constant, take it outside the integral. Integration of rho cube is rho to the power 4 divided by 4. You apply the limits, you get half m r square. So this is how you calculate the moment of inertia of certain uniform objects, starting with the general formula. So you can extrapolate this and calculate the moment of inertia of a uniform sphere of mass m and radius capital R about an axis which passes through the center. You can do this as a homework. So basically what you can do is you can assume that the sphere is made up of a number of disks, or you can divide your sphere into a number of disks of varying radius. You know how to calculate moment of inertia of a disk. So you calculate moment of inertia of all these disks, then you do a summation or an integration, just like we have done in this case. In that way you can calculate moment of inertia of the entire sphere. So that's an assignment for you. In classical mechanics, there is an important theorem known as parallel axis theorem, which is also known as Stainer's theorem, which helps you to calculate moment of inertia of a rigid body about any given axis. So parallel axis theorem states that moment of inertia of a body about any axis is equal to its moment of inertia about a parallel axis through the center of mass plus the product of its mass and the square of the perpendicular distance between the two axes. So imagine that you have a rigid body of mass m. Then according to parallel axis theorem, the moment of inertia about any axis I is given in terms of moment of inertia about a parallel axis which passes through the center of mass, call it as I naught, and the distance between the axes L, or the perpendicular distance between the axes L. So I equal to I naught plus m into L square. So moment of inertia about any given axis equal to moment of inertia through a parallel axis, moment of inertia about a parallel axis which passes through the center of mass plus product of mass and square of the perpendicular distance between the masses. This is the parallel axis theorem. Let's prove this. So assume that you have a rigid body of mass m and you want to find out the moment of inertia of this object about an axis which lies along the z direction. Okay, so about this axis you want to calculate the moment of inertia. So let's prove the parallax theorem using this geometry. As always, you can imagine that the rigid body is made up of a number of particles or tiny mass elements. So you take one particular particle, call it as the jth particle, let mj be the corresponding mass element, and the position vector from the z-axis to the jth particle, you call it as rho j. So rho j is defined as xji cap plus yj k cap. And what about the moment of inertia of the jth particle about the z-axis? This is nothing but mj rho j square, right? So you can calculate moment of inertia of each of the mass element, then do a summation, then you get the total moment of inertia of the rigid body, which is given as I equal to summation over j mj rho j square. Now, you know how to calculate the center of mass, right? You choose a point where you assume that the entire mass of the body is supposedly concentrated. Okay. So let this be the center of mass, and its position vector capital R with respect to the origin is given by xi cap plus yj cap plus z k cap. Now, the vector perpendicular from the z-axis to the center of mass. If you look at the geometry here, z is fixed, so this particular vector r perpendicular, it has only x and y components. So the perpendicular distance vector r perpendicular is defined as xi cap plus yj cap. Now you imagine that there is an axis which passes through the center of mass and it lies parallel to our original axis, which is the z-axis. So these are the two axes. So let's say the vector from the axis which passes through the center of mass, which is the dotted line. So vector from this dotted line to the jth particle is rho j prime. So you have two position vector. One is rho j, which is with respect to the original axis or the z-axis, and second one rho j prime, which is with respect to the axis that passes through the center of mass. And the moment of inertia of the body about this axis is nothing but summation over j mj rho j prime square. So you have defined I with respect to rho j and I naught with respect to rho j prime square. Now you need to find out what is the relation between I and I naught. So if you look at this geometry, as I said in one of the previous classes, you can translate a vector parallelly. It doesn't change the geometry. So you can move r perpendicular to this point, and when you look at the geometry, now you can see that r perpendicular, rho j and rho j prime, these three vectors form a triangle, and using the rule of vector summation, you can see that rho j equal to r perpendicular plus rho j prime. Now going back to the original definition of I, which is summation over j mj rho j square. Now instead of rho j, I can write rho j prime plus r perpendicular. Now expand this product, you get summation over mj rho j prime square plus 2 rho j prime dot r perpendicular. This is a dot product because we are talking about two vectors here, plus r perpendicular square. Now the term in the middle, this becomes 0. How? If you look at the term, this is summation over j 2 into mj rho j prime dot r perpendicular. If you look at this term, summation over j mj rho j prime square, this is going to be 0 because Rho j prime is the position vector with respect to center of mass, and from the very definition of center of mass we know that mass is uniformly distributed around the center of mass, which means if you take this kind of a summation over all the position vectors with respect to center of mass, this is going to be 0. It's like you take a circle, a uniform circle, and for a radius vector in any given direction you can always find a negative vector, right? A corresponding negative vector. So when you take the summation of those two vectors, it's going to be 0. It's almost the same principle here. So here also, since the mass is uniformly distributed, this kind of a summation is always going to yield to a 0 result. Okay, so the middle term vanishes. So my moment of inertia term gets simplified as I equal to summation over j mj rho j prime square plus r perpendicular square. Now expand this, you have summation over j mj rho j prime square plus summation over mj is nothing but the total mass m, so m into r perpendicular square. So r perpendicular is the perpendicular vector between these two axes, and if you take its magnitude as L, then you can rewrite the equation as I equal to summation over j mj rho j prime square plus ml square. Now what is summation over j mj rho j prime square? This is nothing but I naught, the moment of inertia about an axis that passes through the center of mass. So we have proved that I equal to I naught plus ml square. This is the proof of parallel axis theorem. Now we can quickly check whether this theorem is correct. Let's take the case of a thin stick. So we have shown that in the case of a thin stick, its moment of inertia about an axis that passes through the midpoint is 1 over 12 ml square. Now if the stick is uniform, the midpoint is nothing but the center of mass. So you are basically talking about moment of inertia about an axis that passes through the center of mass. So this is your I naught. Now if I shift the axis to one of the ends, then I know the result moment of inertia equal to 1 over 3 ml square. So basically you are talking about an axis which is at a distance L by 2 with respect to the center of mass. So the perpendicular distance here is L by 2. So with this understanding, let's cross check our parallel axis theorem. So I know that I naught equal to ml square by 12, and the perpendicular distance between the two axes is L by 2. So according to parallel axis theorem, the moment of inertia about an axis at the end Ia equal to I naught ml square by 12 plus m into L square, which is L by 2 whole square. So when you do this math, you get ml square by 3, which is what we have derived here. Okay, so we have proved that, or we have shown that the parallel axis theorem is indeed true. So you can use this parallel axis theorem to find out moment of inertia of various objects. Let's do one more example. We know the moment of inertia of a disk about an axis which passes through the center is half mr square. So using this idea, we can calculate moment of inertia about an axis which passes through the ring. So these are the two axes. So the axis through the center also happens to passes through the center of mass. So mr square by 2 is nothing but I naught. And the perpendicular distance between these two axes is the radius of the disk capital R. So you can write Ia equal to I naught, which is mr square by 2 plus m into L square, which is m into r square. So this is 3 by 2 mr square. So using Parallax's theorem, you can easily find out moment of inertia about any given axis. So that's for today. In the next class, we will analyze the dynamics of pure rotation. Thank you.